Welcome, you guys. How you guys doing?
Good.
Doing okay? The middle of the first week back, getting used to things again? Okay. Today we're talking a lot about light. Okay. Now we're going to start with the first half of today's session. It's going to be about the brief history of science with an emphasis on biophotonics. This brief history will be presented by our local historian, Professor James Shackelford, co-instructor of the course. Then we will move on to the photons properties, and then we're going to do the quick whirlwind tour of the electromagnetic spectrum, just to get you guys used to the ideas of how we call those parts of the spectrum, what kind of energies are there, what kind of wavelengths are there. And if we're fortunate, we're going to, during the break between the two different segments, I'll be able to connect the infrared camera. We'll get it to work for sure, but hopefully I can project it onto the big screen. That's what I'm still working on. Okay, so without further ado, next one.
So we'll spend a little bit of time talking about the history of science. Turns out that actually, if you look at the history of modern science, it dovetails very nicely with the topic of the course and all the things we're talking about in biophotonics. And again, my kind of simple-minded definition of biophotonics is that it's really almost a 50-50 blend of the biological sciences, the bio part, and the physical sciences, the photonics part, and then after the run-through of the scientific history of the last 400 years, roughly, then Marco will zero in on exactly what we mean by photons and look in some detail at the entire electromagnetic radiation spectrum. So. Again, what we might call modern science really is largely defined by the invention of the microscope. We have some names and dates here that reflect the early pioneers in this regard. There's some controversy as to exactly who was the very first scientist or group of scientists that actually invented the microscope. One of the things you'll see, you probably heard some comments from Dr. Matthews last Monday. But one of the key achievements of the Center for Biophotonics at UC Davis has been to push the limits of microscope technology. But much of what we experience, your recollections from looking, say, microscopes in a high school biology class, is an instrument that is essentially only slightly changed over the last 400 years. Again, we're starting to ramp up with some significant improvements over the last few years. As much as any, the Janssen family, father and son team of spectacle makers, glass makers, back in the late 16th century, were credited with the first optical microscope. Eyeglasses were known. As Marco knows, most great things come from Italy, so eyeglasses really began were first available in Italy in around 1300s, and so eventually some creative people realized that if you put a set of lenses together, you can do magnification of one type or another. So the primitive telescopes and primitive microscopes are coming along about the same time. So again, the Janssen family, father and son spectacle makers, are often credited with the first microscope. A little bit of debate about that, so I'll put first in quotation marks. Other early pioneers, Robert Hooke, the great British scientist. Those of us in the physical sciences, and material science world, think of him in terms of Hooke's law, basic description of how materials deform under elastic behavior. He worked in a lot of areas, and looking through one of the early microscopes at the structure of cork, that kind of porous wood that we're all familiar with, he saw that fine structure that reminded him of the little cubicles that monks lived in the 17th century, and so he used the term cell. That cell was the name of the rooms individual monks lived in, and that's stuck with us ever since. And so it's really, even though I think of him as a physical scientist, he was someone who gave us a term that has been a central one in biology for ever since. The first person to really systematically and extensively use the microscope to look at biological materials was von Leeuwenhoek, a Dutch scientist, and we'll see a picture of him in a second. So he's credited as the father, to some extent, of microscopy, but certainly of microbiology. So everything we do today, looking at biology on a microscopic scale, really goes back to his pioneering work. And then for strictly selfish reasons, a couple hundred years later, I would say that in my own field of material science, the person who is unambiguously considered to be the founder of that field of looking at engineered materials in a scientific way was Henry Clifton Sorby. At that time, he was in Sheffield, England, lived his entire life in Sheffield, England, in the center of the steel industry in that country. And so he was the first person to look not at biological materials, but at the structure of structural steel under a microscope. And so, again, he's considered the father of metallurgy from that date in 1863 when he made those investigations. And now the field of material science is growing out of that, looking at both metallic and non-metallic materials. So an example of that very first generation microscope, just really a cylinder with a couple of eyeglass lenses in it that were configured so that it would provide a little bit of magnification beyond the limit of what the human eye can see. I think Marco can probably amplify this, but I think the human eye unaided can see about 1/10 of a millimeter, something like that, very roughly. And so the ability to go beyond that, of course, was a significant leap. And so again, a simple adjustable compound microscope like this allowed people to move beyond that limit. The ultimate limit for microscopes, I think we made some mention on Monday. We'll hear a lot more about this as the quarter goes on. And for any kind of observation is typically considered to be about the wavelength of the radiation that you're using. So for visible light, which is in that 400 to 700 nanometer range, we can anticipate seeing objects about that size. So that means that microscopes are typically limited to about a 2,000 times magnification. That's about as much as you can get out of traditional optical microscopes. And then later in the quarter, we'll see some of the very clever things that have been done with microscopes in the Center for Biophotonics, where people have moved an order of magnitude or more beyond that limitation. But in any case, early on, they were just getting a little bit beyond that 1/10 of a millimeter type scale. Here's von Leeuwenhoek, the father of microbiology, a very dapper dresser back in the 17th century. As time went on, another 100 years, microscopes were increasingly sophisticated, and designs that don't look radically different than what we would see again in a biology laboratory today. This in England in the 18th century. And then again, the father of my profession, Henry Clifton Sorby, in the late 1800s, a short while after he had done those pioneering inspections of metals under a microscope, he's on his yacht, the Glimpse. I think that title probably had something to do with his fondness for microscopes. Interesting guy. He was very wealthy. He was born into wealth and inherited the family. Father died early on. He was about 21 years of age. He inherited the family fortune, and instead of just going off to London and being a gadabout, he decided to devote his life to science. So he stayed in Sheffield, England the entire time and devoted himself to learning more about the materials of importance to the steel industry in that region. And he made major contributions not only to metallurgy but also to geology. And again, but he had enough wealth to enjoy himself on the side on the family yacht. Then looking at a little more recent time, what we might call the era of modern physics, really the story of the 20th century was the ascendancy of modern physics and all the stuff that happened around the break in time between the 19th and the 20th century. And I know you're all familiar with the highlights of that story. probably most celebrated scientist, of course, being Einstein. When Time magazine chose their person of the century for the 20th century, it was Albert Einstein, because he was sort of a metaphor for all the new thinking and the groundbreaking radical ideas that came into the 20th century. Well, and contributions to making that all of the creative thinking that Einstein did possible were a number of pioneers, and so I have about a half a dozen names here, a little over half a dozen names for dates running from just before the beginning of the 20th century up to the middle of the 20th century. And we could call that the half century of physics. Physics was the premier science at that time. And as I said, biophotonics is kind of a unique topic and an ideal topic in a way in terms of appreciating modern science, in that it's this almost perfect blend of the physical sciences and the biological sciences. And so historically, the first half of the 20th century was dominated by physics. Headlines in newspapers, the big cultural events, the big social impact of science on society in general was happening from the world of physics. And to a large extent, predating the great discoveries of Einstein, I'd say was really the year 1895, when Professor Röntgen in Germany discovered the X-ray. That little image in the upper right-hand corner is, we'll see that again, that's the world's first X-ray. If we define X-rays not by the part of the electromagnetic spectrum as the short wavelength photons, but as those things that we get when we go to the doctor and they take a chest X-ray, or if we break our elbow and have a X-ray made of the arm to see where the break is and that kind of thing. Those photographic images, essentially shadowgraphs that we call X-rays, are all go back to the discovery in 1895 by Professor Röntgen in his little laboratory. The hand shown there looks like, again, a kind of a typical medical X-ray, kind of a low quality one, kind of a grainy picture, but it has the distinction of being the first X-ray ever taken. That's his wife's hand. The little funny bump there on the second finger is her wedding ring. He basically said, Frau Röntgen, would you mind coming into my laboratory? I'm getting a strange glow off of this experiment I'm doing. I'd like to see if what we might be able to do with this. And so he took an X-ray of her hand. Scared the hell out of her. She never went back into his laboratory after that. It's really quite an interesting sidebar. But nonetheless, it made him the most famous scientist in the world. This photograph was essentially replicated on the front page of virtually every newspaper in the world. It was the first time in human history that someone had been able to look inside the body of a living human being, and it was just a tremendous revelation that obviously the general public could see the impact of instantly. And obviously it's become a ubiquitous part of modern medicine ever since. And of course the X-ray, called it X-ray because it was an unknown quantity. You really didn't know what he's dealing with. Now we know it's just part of the electromagnetic radiation spectrum. Mark will go into that in detail in the second hour. And obviously has a tremendous number of applications. We'll see at the end of my little recap of history that it also led to the launching of the second half of the 20th century as the half century of biology that we're still in the middle of right now. Interestingly enough, just 2 years later, an equally profound discovery was the discovery of the electron. Again, it's kind of hard to imagine, especially for me, young people, all of this is ancient history. But for me, looking back at the dates in the early part of the 20th century is not such a such a distant past, and think that over a period of 100 years, really the lifetime of a lot of people, it's not so uncommon for people to live to be 100 years. And so think back over that period of 1 century that we've gone from the kind of ubiquitous presence of modern electronics in our everyday lives to the fact that we didn't even know what an electron was until the latter part of the 20th century, or the latter part of the 19th century. So again, within a 2-year period, 2 landmark discoveries were made that really set the stage for all of those developments in the early part of the 20th century that we think of as, again, modern physics, the relativity, the quantum mechanics, and so on. So it's J.J. Thomson in England who did made the discovery of the electron and sorted that out as a subatomic particle, which again has had enormous impact on modern society. We'll also talk for a second about Ernest Lawrence. I put the date 1939 there, not because that's when he discovered or invented the cyclotron. It was done about a decade earlier, but that was the year in which he got the Nobel Prize for his discovery. Whenever I give this little talk, I always pay homage to Lawrence with a kind of hyperbolic statement that I consider him to be the most important professor in the history of the University of California, and that's a pretty bold statement. We've had a lot of great professors over the years, and a lot of great professors still, but he has a kind of a singular role in the history of the university. Back then, of course, by and large, in the early part of the 20th century, the University of California was UC Berkeley. People down there sometimes continue to think that they're the only campus in the University of California system, but we were always reminded that that's not the case. But they're still our flagship campus, and they were, again, up until the middle part of the century, the only campus in the University of California, by and large. Davis, we've celebrated a centennial here, but we're a little bit of an offshoot. We were sort of the agricultural experiment station for the Berkeley campus in the early part of the 20th century. The Berkeley campus was pretty much the whole institution. And Lawrence was recruited as a young faculty member, actually recruited away from Yale, which is kind of a bold step to leave the prestige of the Ivy League and come out to what was a very young campus at that time. But he saw the future and the opportunities of the University of California, and the sort of future was in the West, and he was exactly right. And the discoveries that he made and the fact that he was able to be one of the primary contributors to the new physics in the 20th century brought enormous, really almost unquantifiable prestige to the institution. I mentioned in passing he got the Nobel Prize for that. It was not just that he got the Nobel Prize. He was the first professor at a publicly funded university to get the Nobel Prize. So he elevated the reputation of public universities to the point where they're on par with private universities. And that's true today. I mean, if you look at you're all when you're scoping out universities, looking at the U.S. News and World Report rankings and all that stuff. And so the great national universities are all the UC campuses, the University of Michigan, University of Virginia. All these schools are essentially full peers now of the Ivy League schools. In many cases, more highly rated than the Ivy League schools in many areas. And it really, truly all goes back to Ernest Lawrence as having established that level of prestige. And beyond that, not only did he invent the cyclotron, he's widely regarded as the father of big science. We'll say more about that. And then his colleague at Berkeley, not only did Lawrence bring the sort of world-class experimental physics capability to a public university, the University of California, his colleague Oppenheimer was widely regarded as a premier theoretical physicist of his day. And the fact that the two of them were side by side teaching at UC Berkeley at that time also contributed enormously to the prestige of the university. Of course, as we know, Oppenheimer's fame came in another direction when he was recruited away, very surprisingly, this theoretical egghead was recruited away to head the atomic bomb project for the United States, obviously in the race against Germany to develop the atomic weapon, which would obviously have a kind of a concluding influence on World War II. And so Oppenheimer's associated with the Manhattan Project. And then a couple of other dates here that are, I think, critical, kind of wind up this first half of the 20th century and sort of the physics half of the 20th century. One of the last great major breakthroughs in the physical sciences was the invention of the transistor at Bell Labs by those three gentlemen, Bardeen, Brattain, and Shockley. That obviously made our laptops possible. And what's also interesting to me, I think, is that it came exactly 50 years after the discovery of the electron. So again, considering that for all of human history, we really didn't have a concept of subatomic particles, barely struggled with the concept of atomic particles. And so with 1897, the discovery of the electron, then exactly 50 years later, the advances that were made in physics and electrical engineering to invent the transistor and open up the era of solid-state electronics, and then the kind of rapid pace since then, for now we can walk around with the capabilities of an iPhone and those kinds of things. Just a little over 50 years after that, it's really astounding. Also put in a non-scientist, Harry Truman, President of the United States after World War II, 1950. There's a very important date there, the development, or the launching of the National Science Foundation. And this is important in scientific history because that helped to amplify the kind of work and contribution that people like Ernest Lawrence made to modern science. I said Lawrence is credited as being the father of modern of big science, the large-scale, national laboratory-scale scientific inquiry. He did that very much on his own, if you will. He was just a master at going back to Washington, D.C., talking to congressmen and convincing them that major investments, millions of dollars, and when millions of dollars went a lot farther, he was bringing back from Washington millions of dollars to build larger and larger cyclotrons, particle accelerators at Berkeley, to advance experimental physics, particle physics. What Harry Truman did as president was to essentially acknowledge the wisdom of that and the quality of science that was coming out of it in order to have a national agency, a government agency that's devoted to doing that in a systematic way. And so ever since, that has been a primary source of research funding at major research universities like University of California campuses, and in fact it's the source of the funding for the Center for Biophotonics. So that's more than just a minor relationship to what we're doing here in CBEST. So that's Professor Rankin and his wife's hand there, the very first radiograph. This is the paper that Professor Thompson published in the Physical Philosophical magazine in 1897, talking about his experiment. He was basically, refers here to cathode rays. This was really an experiment in a primitive version of an old television tube. He was accelerating electrons into a vacuum, into, again, something that looked very much like a television tube, and then observing on the screen what was occurring, and sorted out that those particles being accelerated that were creating the phenomena on the screen were basically negatively charged particles that had to be components of the atom. And so it really opened up the whole idea of particle physics. And then Ernest Lawrence, the inventor of the cyclotron, the father of big science, as I said, the first Nobel laureate from Public University. And then Robert Oppenheimer, the father of the atomic bomb, and he gets singular credit for that. As I said, he was a uniquely surprising candidate to manage any project. He was a theoretical physicist, someone who was considered to be probably the most brilliant scientist in the country, and because of that, that's why General Groves, who was the Army general in charge of this secret effort to develop an atomic bomb, he recognized that even though Oppenheimer had no administrative experience, he had the absolute respect of the entire physics community. So he turned to him, Groves turned to him, to be someone who could bring the best scientists in the country, and in fact in the world, to this secret location in New Mexico to carry out this project. And he was surprisingly successful and surprisingly dedicated and skillful as an administrator. He threw himself into it completely. The reason that there was this open competition was because of the success, how much people had learned, how much the physics community had learned about the nature of atomic physics by the late 1930s. The specific discovery in Germany, which made us especially fearful of the Germans' ability to develop an atomic bomb, was the discovery of the phenomenon of fission. That is, the spontaneous decomposition of nuclei, where they break apart and send neutrons off in flying out of the atom, which could then split other atoms nearby and create a chain reaction. Once that phenomenon of fission, atomic fission, nuclear fission, was discovered, then it became clear that the atomic chain reaction was possible. And there are two possibilities once you realize that. And it became crystal clear to the physics community what those two possibilities were. The first, if you do it slowly, in a controlled way, you can generate a tremendous amount of energy from that. So the nuclear power plant design is an obvious concept that follows from that. If you do the chain reaction very rapidly, then you have an explosion vastly greater in power than conventional weapons. And of course, that's the weapon of mass destruction that we all worry about today, and fret about the fact that India and Pakistan both have these nuclear weapons. Soviet Union and the United States still have 7,000 to 10,000 deployable nuclear weapons in their arsenals. Scares the hell out of everybody. But it was crystal clear in 1938 that the paper that was published that identified the phenomenon of fission opened up that entire world. And so when World War II began, it was very clear that this was a possibility. And so there's fascinating histories of this that you read about what evolved, but the result was that there was this essentially secretive race, primarily between the United States and Germany, and clearly it was the United States that was successful, and it was Oppenheimer who had the dubious distinction then of being the father of the atomic bomb, because he managed our project so successfully. It was Heisenberg on the German side who was but then as we move into the second half of the 20th century, up to more or less the current time, we see a significant shift. I'll add one more prominent physicist to this, and that's Edward Teller. He is I put the date 1952 on his long life. He actually just passed away in 2003, and at the age of 95 or so, had a very long life. he was also a University of California professor, but not a UC Berkeley professor, but a UC Davis professor. And he, along with Lawrence and Oppenheimer, formed a kind of troika of the great physicists of the mid-20th century who, by and large, were responsible for the really the modern era of nuclear weaponry and the launch of the National Laboratory System, which initially was associated with weapons production, but now is a much larger, largely peaceful application of scientific knowledge, both physical sciences and biological sciences. So I put the date 1952 there because that was the year that he successfully talked the federal government and the University of California into opening a second weapons lab in Livermore, California. It was called at the time the UC Radiation Laboratory, and since that time, after the passing of Ernest Lawrence, it was named in his honor, so it's the Lawrence and Livermore National Laboratory, and there's also, of course, the Lawrence Berkeley Laboratory down at next to the Berkeley campus, also named in Lawrence's honor. So those two great national laboratories came out of the pioneering work of Lawrence and then also the weapons work out at Livermore. And the legacy of Oppenheimer was the secretive laboratory of Los Alamos lived on to this day as the Los Alamos National Laboratory. That was really the first of the great national laboratories. And now there's an infrastructure. If you go to the Department of Energy website, there's a network of 10 of these national laboratories managed by various entities, 3 of them by the University of California, Los Alamos, Livermore, and Berkeley. But shortly after the Livermore lab was opened, then the paper that changed everything was published, 1953, April 1953. A one-page paper by James Watson and Francis Crick opened the modern era of biology. So from that point on, the headlines in the newspapers that talked about the impact of science on society largely shifted from physics to biology. And it continues on to this day. You see headlines about cloning, about stem cell research, a lot of political controversy about all this stuff. It all goes back to one-page paper published in 1953. We'll look at that in a little more detail later. Physics wasn't dead, though. Charles Towns got the Nobel Prize in 1860 for his invention of the laser. We'll see lots and lots and lots of applications of lasers in biophotonics. And then as kind of an indication of the kind of accelerating pace of things, as I said, 1897, the electron was discovered. 1947, exactly 50 years later, half a century later, the transistor is invented. And so for the next quarter of a century or so, solid-state electronics is advancing very rapidly. Of course, it was invented, the transistor was invented at Bell Labs, and so they and the other big corporations, AT&T and the other big corporations, making lots and lots of progress in terms of solid-state electronics, but they're doing it all with separate components. And so in 1971, Jack Kilby at Texas Instruments and Robert Noyce at Intel Corporation simultaneously, this is now about a quarter of a century after the invention of the transistor, come up with the concept of putting transistors not as discrete elements in a circuit, but basically laying them down in a miniaturized version of what artists do in making a lithograph, essentially painting these circuits on semiconductor chips. And so the integrated circuit was invented, and Noyce didn't live to see it, but Kilby lived long enough to get the Nobel Prize for that invention, and of course with obviously the kind of ubiquitous role that it plays in our lives. So the integrated circuit has now led to, again, all the miniaturization, the fact that we have laptops and iPhones now, as well as transistor radios that we had at one time. Another kind of administrative red letter day red letter year, was 1987. I put that down because that's relevant to biophotonics and the fact that we have a Center for Biophotonics at UC Davis. That was an interesting development in the history of the National Science Foundation. Again, National Science Foundation was launched by Harry Truman in 1950. So it was a systematic way to provide government funding to university researchers in the way that Ernest Lawrence had kind of done it on his own for so long. In this now 37 years after the launch of the agency of the National Science Foundation, they had a director named Eric Bloch. He had come from not from academia, but from IBM Corporation, and he was looking around at the context of the country at the time and said, as wonderful as the National Science Foundation has been and the fact that it's provided funding to university researchers for so long, it's provided an unbroken string of Nobel Prizes. If you go to the Nobel.org website, working on term papers in science classes and so on, that's a great source to find a nice background material on all these great scientific breakthroughs that have been awarded with the Nobel Prize. And look at that, at the winners of the Nobel Prize over the years up to this day, a steady stream of Americans, and many of them, probably most of them, have been supported by research funded by the National Science Foundation. And Eric Bloch said, that's great, but I come from the industrial world, and now in 1987, we're taking a beating, and we're taking a beating from Japan. And why are we taking a beating from Japan? Well, because they are outcompeting us in the marketplace. They're outcompeting us in the industrial workplace. And how are they doing that? Well, they may not win as many Nobel Prizes as we do in 1987. They'll occasionally get one, but they're putting these ideas into practice, and they're making practical products, and they were beating us in selling electronics. This is before the Chinese Revolution, and at that time, 20 years ago or so, they were the ones, the Japanese are the ones that were beating us in so many areas of cheaper electronics, the Sony radios, the Sony televisions, and so on. And so he's in looking at the way the Japanese were doing their research and development, he saw a lot more level of cooperation, and he saw the scientists working with the engineers, and saw them working with entrepreneurs and getting ideas into the marketplace in a much more efficient way than we were in the United States. And so he launched something called the STC program. The STC program stands for Science and Technology Centers. And it was a big break. It was very controversial. A lot of scientists hated it. And the reason they hated it is for 30-some years, they had been able to write proposals to the National Science Foundation as individual investigators, world-renowned scientists, and they would write a proposal, have a good idea, it would get funded, they would hire graduate students, they would get the research done, they would win their Nobel Prizes. So what's wrong with this picture? Nothing, they would say. But again, Eric Bloch is saying there is a problem because, again, this isn't contributing to the national good in the way that it could possibly, in the way that some countries, such as Japan and Germany and some European countries, were doing better than we were in terms of getting things into the marketplace. So science does not live in isolation. It also should be contributing to the greater good. So he said, we'll have these science and technology centers. I'm going to take some of the money that would have gone to these individual investigators and have them compete not as individual scientists, but as groups of scientists. And it turned out to be a very successful program, and it's one that goes on to this day. And so again, the Center for Biophotonics, Science and Technology is one of these centers. And again, Dennis Matthews showed you one of, I think, about 17 centers now nationwide. At any one time, there are about a dozen to 20 of these in the United States. And so again, we're one of about 17 right now. So the CBEST program is typical of this. And so I found out the last historical figure is our guest speaker on Monday, Dennis Matthews, as an example of this. And he's also a very good example of all things we talked about so far. He's kind of a metaphor. He's a pretty modest guy, and he'd probably blush if he was here now, but he's an excellent example of what we've been talking about. In fact, he kind of replicates this whole historical picture of the last century. He started out as a physicist. He was a physicist at the Lawrence Livermore National Laboratory, in fact, and he was a laser expert. And he worked on problems in the first part of his career, many years of his career down there, in weapons programs. And he worked on the issues around the Star Wars defense system and all that stuff in the 1980s. And he decided to make a kind of a career change after that point. And said to himself, he commented on this on Monday, that decided to, instead of just designing products that would blow people up, that he would maybe work on things that could make people feel better. And so he moved over to the medical physics area and began to work and apply his laser technology to issues that could improve human health. Began to work with the Cancer Center at UC Davis and became increasingly involved in work in that area. And so the result of that is that the Cancer Center at UC Davis now has a National Cancer Institute designation, which is a very prestigious level of achievement for that center. And the director, Ralph DeVere White, Dr. White is a huge fan of the Lawrence Livermore National Laboratory, not because they used to make design atomic bombs, but because they are contributing to human health in a very unique way. And the reason it has NCI designation is because it's in a very effective way, largely through Dennis's contributions, combined advanced technology, especially laser technology, to cancer diagnostics and therapeutics. So it really rounds out this very nicely. So just to put a couple of pictures with this. This is Ed Teller, who was again the third of that great triumphant of mid-century, mid-20th century physicists who played a key role in the dawning of the nuclear age. He has the dubious title as Oppenheimer is the father of the atomic bomb, the fission weapon. He was the father of the hydrogen bomb, the fusion weapon. And there's also tremendous sidebar stories about his rivalry with Teller, which we'll leave to another time. But he is the founding chair of the Department of Applied Science at UC Davis. And so the optical science and engineering major at UC Davis is managed through here. And it's basically a program that relates very closely to the work of the Center for Biophotonics. The chair of the department, Yin Ye, is a very active member of the Center for Biophotonics. And then we'll close out, as I said, with the paper that changed everything. And in fact, their paper, April 25th, 1953, page 737, the most famous paper in modern biology, in which they basically took X-ray diffraction patterns that had been made of DNA material, and in a very fierce competition with fellow scientists around the world, decoded the structure that would have created that particular pattern. So what people were doing at that time, they knew that DNA was an important component of the biological system, but they didn't know exactly what the nature of that role was. And one of the underlying principles of modern science is, in general, the structure of the material on the atomic or microscopic scale determines the function of that material on the macroscopic scale where it matters to us as human beings. And so it was critically important to determine exactly what that molecular structure was. But this is a point in time over 50 years ago when analyzing structure was very difficult. It was, believe it or not, before the age in which we could just have all this sophisticated structural analysis done by computers. It had to be done by hand. It was a laborious exercise, very tedious, and very difficult to solve these structures, especially in complex materials. And there's an excellent book, one of the most famous books of the 20th century, written by James Watson on his recollections of this competition, this very fierce competition among the leading scientists of the world. Their main competitor being Linus Pauling, who had already won 2 Nobel Prizes. They were all working on this structure, but it was Watson and Crick that came up with the fine Lancer, which, as everybody knows, is a double helix, which is the title of Watson's book. And this is a one-page paper in which, again, they had not done the experiment. Others had made those experiments. They were publicly available. And the race was on just to decode what that structure meant, or what that diffraction pattern meant. And the structural answer was, it was a double helix. And this little cartoon that they drew is the result, that those 2 molecular ribbons that were tied by these base pairs in this spiral staircase pattern was the explanation for that diffraction pattern. And they have 2 great lines here at the opening, kind of masters of understatement. Francis Crick was British, and sure the source of that, James Watson, was an American postdoc over there at the time at the Cavendish Laboratory in Cambridge, England. And they said, we wish to suggest a structure for the salt of DNA. This structure has novel features which are of considerable biological interest. And then toward the end, they say, it has not escaped our notice that the specific pairing, this little set of base pairs here, briefly bonded in the double helix, which can be unzipped and lead to the genetic duplication that you're going to be hearing about in detail in a few lectures. It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. And of course, 1962, they get the Nobel Prize, well deserved. Almost surprising, I suppose, it took almost 10 years for them to get that recognition, because it was so clearly obvious that this was the answer to the questions that everybody had. And so then, since that time, it's been a really the foundation of everything we've done in modern biology, and biology has now become the dominant science as a result. So we'll take a little 5-minute break, and we'll reconvene with the electromagnetic radiation.
The first lecture that was done yesterday, our VCR, our online VCR ran out of space, so we were only able to get the first 45 minutes. But I will post a lecture that Professor Matthews gave. Let me double check this thing here. Still recording. Okay, good. Okay. So we got the whirlwind tour of science with the biophotonics perspective. And now we really need to spend some time thinking about light. Okay? This is the important element now. Now, when we talk about light, the most critical unit that we talk about is the photon. Okay? Kind of everything centers around the photon. And why is that? Well, it's the smallest unit of the electromagnetic field. Right? It's the quantum. And the photon has a really interesting property in that it can behave both like a particle and like a wave. So what does that mean to you? You guys tell me what does particle behavior mean and what does wave behavior mean? Can you give me some examples, some ideas that you might have about that?
It has a wave that has interference patterns, and if it's a particle, it's very targeted and very good.
Okay. You guys, any other ideas out there? if I was to have a little BB gun and shoot at a target, are those BBs behaving like particles or waves? Okay. Have you guys ever been out and you're at the ocean and you see a long pier and you see waves coming in, or a seawall, anything like that? You see those wave fronts, when they're coming in kind of regular. What happens when they hit a barrier? Sorry? They go back out. What else happens? Like, let's say that you have a wave coming in and you've got this kind of barrier in the middle of it, but there's still water on both sides and the barrier is kind of isolated. What do you think happens to the waves? Do they stop? Some bounce back. And what else do we see? You get some absorption, we get some loss of energy. But do those waves, so let's do this thought experiment, okay? We get this wave coming through this class, and you guys are the barrier, okay? You two, that desk is the barrier. So the wave is coming, hits these guys. What happens to the wave? It goes around. Okay? Now, if instead of a wave, I've got a whole bunch, I got the back row all with BB guns, okay? Shooting them. Well, not harming anyone, but shooting these particles. What would happen to those BBs? They would stop wherever these guys are, right? They wouldn't come by you guys and then come back around. So if I had a piece of paper here and I was getting all the holes from the BBs, would I have holes here? Would I have holes here? Here? So, you see, these guys would have stopped the particles, but the wave would have gone around and come back. Okay? So, light behaves in both of these ways. So, we call this the wave-particle duality. Okay? And the funny thing is, depending on what property you look for in the photon, you either observe the particle properties or the wave properties. Okay? So you can kind of tailor what you're looking for in the properties of the photon. Now, normally light is formed from a large number of photons, and the intensity is related to the number of them. So when we have very few photons, we think of it as being dim. When we have a lot of photons, we think of it as being bright. Okay? Our eyes need somewhere in the order of a few hundred photons to detect light. So when you guys are out on your moonless night and you're out in the wilderness, total dark, there's still starlight. But let's assume total dark, you're inside your tent, fully dark. Your eyes could pick up maybe 100 photons. If 100 photons hit your eyes simultaneously, roughly at the same time, you would see them, you would register them. But if only one photon hit, then a few seconds later another photon hit, and a few seconds later another photon hit, you wouldn't see it. We have instrumentation that can see that. Okay? And part of what we do in biophotonics is we use instruments that can detect very, very small numbers of photons. Okay? Okay. So, some properties of photons. Photons are commonly associated with visible light, but this is actually only a very limited part of the electromagnetic spectrum. So when we talk about the electromagnetic spectrum, and we'll talk about it more today, we talk about things like X-rays, gamma rays, radio waves, microwaves, infrared, ultraviolet, visible. Visible light, what we tend to think of as light, is only a very small portion of the electromagnetic spectrum. But in reality, the electromagnetic spectrum is huge. There's a whole range of energies and wavelengths of photons. So, all electromagnetic radiation is quantized as photons. That is, the smallest amount of electromagnetic radiation that can exist is one photon, and the energy of it depends on its wavelength or frequency. These two things are interrelated. Photons are fundamental particles. That means we cannot break them down further. They can be created and destroyed based on interacting with each other, but they don't decay on their own. So that star way out there, billions of light years away, that we're seeing, the photons that left that star have traveled for billions of years without decaying. Now we've lost some of them to intervening objects in space, to space debris, to gases in space, to all kinds of other things. We've lost some of those photons. But the ones that made it to us, they're still what they were when they left. There's been no decay. There's been no change. Okay? They came from billions of years ago, and we're seeing them now because they traveled that far. Okay? Now, the other really weird thing about photons are kind of this mystical thing to me. Okay? They have no mass. But somehow they still have momentum. And what I mean by that, they can still pack a punch, but they have no mass. We tend to think of...
Is that what they say when they talk about solar winds being used on spacecraft?
They're talking there about certain types of particles being able to push. And it can be, you can use light pressure too. So you can have some pressure, some push, some momentum imparted from the energy that these photons have. But they're usually talking about a whole range there. I don't think they're just talking about photons. I think they're talking about other types of particles too. To think about that. It's a good question. So without having any mass, they still can impart a punch. Okay? I can actually use photons to trap something. And we do. At our research facilities, we trap cells and little tiny beads with laser beams all the time. So we're imparting momentum, we're trapping something. We can also cut, we can push, okay? We can nudge things over, all with photons, even though they have no mass. So it's as if I were to punch you in the arm, you'd move, but my arm had no mass. Kind of strange. Okay? But this is one of the interesting properties about photons. Now, photons are always moving at the speed of light with respect to all observers. They have both energy and momentum proportional to their frequency or inversely proportional to their wavelength. So what does that mean? If their frequency is higher, do they have more energy or less energy? More. Okay? If their wavelength is larger, do they have more energy or less energy? Less. Okay, perfect. Okay? Now, the momentum can be transferred when a photon collides with matter. And that's where I'm telling you that I can use these photons and transfer their momentum to some kind of particle, trapping it, pushing it, moving it. Okay? Kind of an odd thing. Very interesting. So how do we create photons? The most common way that we talk about a lot in this class will be when a bound electron moves from one orbital to another orbital with less energy. Okay? So what happens, you guys all had chemistry back in high school? Do you remember that atoms have electrons effectively going around them in different orbital configurations? When they move from one energy level to another, if they move up in energy, they become more excited. When they get back down to their base energy state, they release a photon. Whenever there's a transition from a higher energy level to a lower energy level, there's a release of a photon. And that photon we care a lot about. We do a lot with those photons. They can also be emitted by an unstable nucleus when it undergoes some type of nuclear decay. They're produced whenever charged particles are accelerated. Not quite as important. Most important, atoms continuously emit photons due to their collisions with each other. The wavelength distribution of these photons is related to their absolute temperature. Remember, I'm trying to remember, did we talk about black body temperature? Remember with the thermometer that went across your head? We talked about atoms moving, vibrating. They're vibrating, they're colliding, okay? Those collisions, those vibrations lead to collisions, which always lead to emitting photons. That's why every single thing that vibrates and is near some other atoms and can impact them causes the emission of photons. Okay? Hence why everything that we know of, except total empty space, is emitting photons of some kind or another. We just don't know in which part of the spectrum. Yes? Neum, is that? Neve. Okay.
Are you going to post these lectures online?
Yes.
Like the
Yesterday's and today's will be posted. I'll try to post them later today.
Well, the PowerPoints as well.
Yes.
Oh, awesome.
Yes. Actually, the PowerPoints will get on there faster because the other talks usually need a little bit of cutting on the edge of the actual video talk. It needs a minute. Okay. So, Visible light is a mixture of many photons of different wavelengths. Okay? So what we think of as visible light, the way I see you guys in all the wonderful colors that we have around us, that's only a small portion, and it's a mixture of wavelengths, primarily from about 380, 400 nanometers in wavelength, all the way up to about 720, 750. We all have slight variations in exactly how blue we can see and how red we can see, how far in the infrared we can see. There is some variation between us. And an assembly of photons can exist in, so when you pass that light through a spectrum, you can see it all separated into its component colors, the different wavelengths. Right here, it's just showing you a prism in a wavelength representation. And you see all those waves are actually going in all different, can all go in all different directions. They're different wavelengths, which means they're different energies, and they're not necessarily coherent. They don't know about each other, they're not interacting with each other. But we can also create things, bless you, we can also create things like a laser. And in a laser, we can make the wavelengths all be the same, or very, very close, so they're all the same energies, and we can make them travel coherently, so they add to each other and they make something that's very bright. Okay, but we'll be talking about that more as the course progresses. Don't worry about it too much right now. Now, just to recap, a photon is a massless particle with energy given by E equals h frequency, okay? H being Planck's constant, and F being the frequency. It's also sometimes labeled as nu. And because frequency can be described by the speed of light divided by the wavelength, this is called the wave equation. And in this case, you can also say that the energy is equal to the speed of light times the momentum. And this is more particle in nature. So you can actually create equations that link the energy of a photon to both momentum and to wavelength. You can make it both of those equations. This equation right here will be one of the few equations that you'll need to know for the course. Okay? I think there may be one other one. Very, very few equations needed for this course. But there are relationships between energy and how energy relates to frequency and how energy relates to wavelength. Those are very critical. Okay? That relationship. The direct versus the inverse proportionality. Okay. When we think about a wave, we think about something that's going like this. And in an electromagnetic wave, the way that wave is defined, it's defined by two components, an electric field component and a magnetic field component. Those two always come together. That's why it's called an electromagnetic wave. So the photons have properties of their field that are magnetic and properties that are electric. Okay? In reality, this is a way of, I don't know how many of you did vectors, but there's two vectors, one in one direction, one in the other. When you add them together, you get a wave. And that's the wave that goes. You have two waves, the vector components in the two different dimensions, they add up to one wave. That we tend to use. We normally only draw one wave when we draw an electromagnetic wave, even though there's two components. Now, again, this part is not a huge deal. So, photon is associated with a wide range of wavelengths, as indicated by the electromagnetic radiation spectrum. One thing that I do want you to know is that a photon is not a particle. It can behave like a particle, behave like a wave, but it is not a particle. Okay? Particles are things like protons, neutrons, and electrons. They have a specific mass. A photon does not have mass. Okay? The funny thing is these particles do have some behaviors of waves. So sometimes we get these things confused. Okay? A photon does not have mass, so it is not like a proton, neutron, or electron. Okay, here's the electromagnetic spectrum. Let's get into the nitty-gritty of the EM spectrum. So, the EM spectrum ranges from radio waves to microwaves, infrared, visible, ultraviolet, X-rays, and then gamma rays. We are constantly bathed in all of these energies. Okay? Right now, if you take your cell phone and wave it around, you are bathing the people around you with microwaves. Okay? That's what your cell phones use. That's what your cordless phones use in your house or in your dorm room. Okay? Radio waves, if you've got a radio, I know we don't have them as much as we used to, but if you had a radio and you tune it, you pick up the radio waves. How can you pick them up? Because they're here. They're all around you. Okay? You're constantly being bathed in radio waves. Infrared. There's heat. Sometimes you have a space heater on the side that's glowing red. You have other things that are giving off infrared all around you. If you're outside, the sun is giving off plenty of infrared that your body's feeling. Visible, we're all familiar with. It's what we see right now. Ultraviolet. Ultraviolet is what causes us to get sunburns. And luckily, most of the ultraviolet is blocked by the atmosphere. That famous, what do you think blocks ultraviolet in the atmosphere? Ozone. Yeah. Why were we worried about ozone holes? Well, because the ozone blocks the high energy ultraviolet light. What does the high energy ultraviolet light do to us? What? How? Sorry? How? Cancer, how? Mutates genetic code. Okay? It actually causes breaks in your DNA, altering the capabilities of that DNA to be replicated appropriately to generate new tissues, new cells. If I disrupt that in enough quantity, then I can create problems. Each one of your cells is doing about 100,000 pieces of repair work every day. Okay? The mechanism in each one of your cells is doing that every day. But if I start doing 120,000 mistakes in each of your cells on average every day, because I'm exposing you to more UV, your body can't keep up. Eventually, many of your cells are damaged. Some of the damages doesn't cause anything. It just causes the cell to maybe live a little less long. Some of it causes it to replicate, but there isn't any major problem that's caused. Some of those mistakes cause cancers. They cause weird things to start happening. Growths of these cells to start replicating uncontrollably. Okay? So really it's a race. Our body's constantly fixing mistakes that are brought upon us from all kinds of things, from the food we eat, from the electromagnetic parts of the spectrum that we're exposed to. And part of what aging is our abilities to repair that slowing down. And that's why there's a whole bunch of research targeted at trying to not affect that slowdown, trying to stop that slowdown. And then that's why people say, oh, we could live forever. If you can stop that from happening, you can live forever. Okay? Now, ultraviolet does that. Luckily, the ozone blocks it, so it doesn't cause so much damage. As we go into X-rays, they do it even more. They cause even more of this kind of damage. And as we go into gamma rays, they basically just obliterate whatever's in their way, if they hit something. Now, the thing that's hard for me and for most people to conceptualize is that we're mostly empty space. Okay? There's a ton of space between all the atoms that make us up. Between the nuclei of all the atoms that make us up, there's a ton of empty space. That's what allows many X-rays and gamma rays to just go right through us without touching anything. You can imagine that. They go through billions of cells, but they don't touch anything. They don't interact with anything. Because we're mostly empty space. I know it doesn't look that way to us. And it is kind of trippy again. It's one of those strange concepts. But we are mostly empty. Okay? Now, gamma rays go through us. They go right through the Earth. They go out the other side. They keep going. Yes?
What's the difference between soft X-rays and hard X-rays?
Just the range of energy. Yeah. Pretty much, you can draw a line somewhere along here in the ultraviolet. And from there onwards, these things are energetic enough that they're labeled as ionizing radiation. If they interact with one of our electrons in an atom, or they interact with any part of the atom that's solid, then they will ionize it. They can strip the electrons from that atom. If you strip the electrons from that atom, or you strip the neutrons from that atom, whatever you strip from that atom, it falls apart. Okay? Falling apart means bonds broken. DNA chain is destroyed. What protein is destroyed. Whatever it is that they interact with. Right? Unless they happen to hit the end of a protein or the end of a DNA, then maybe they don't do so much damage. Okay? But this stuff is ionizing. This stuff in here and in here has different properties. It's called non-ionizing radiation, but it can still be absorbed and interact with biological materials. And that's why we care about it in biophotonics. Okay? So what kinds of things do you think these non-ionizing radiation can do to living things? You have any thoughts to atoms, to molecules? What can they do? Sorry?
Heat them.
Heat them. How would that be done? Sorry?
Conferred light, and that would speed up the molecules out there.
Speed up the molecules, so you're saying increase collisions. Okay.
Well, I mean, when you put something in the microwave, it would speed up the water, the molecules in it, and that causes them to release. If it's 70% water, that would be bad.
So you don't want to sit inside a microwave.
Yeah.
Yeah, and unfortunately, the people that first invented microwaves were kind of generating microwaves out in the middle of nowhere, in the middle of the room, and they did die very early deaths because they basically cooked their insides. Okay, that was a bad thing. Okay, but they brought you microwave popcorn. So they did not die in vain. Yes.
So what happens when you're outside of that range on the spectrum? Are these still gamma waves and radio waves? Or?
You mean this way?
Yeah.
You know, pretty much this is what we know about.
And
Whether there can be something outside, you know, this is what we've been able to measure, see.
And what about the microwave from our cell phones? Is also bad for us?
So, you know, 10 years or five years ago, they started this whole thing about, you know, cell phones are going to give you brain cancer, and people just thought it was the biggest bunch of crock ever. And now they're kind of saying, well, buy a Bluetooth headset or use some other device. Don't stick it close to your brain too often, because the most recent studies that appear to be pretty accurate say, especially to the youth, while your brain is developing, it's even more dangerous. So minimize, you know, sticking it right there.
So texting is good.
Texting is great. Texting is great. Effectively, what it's saying is that, you know, phones have gotten more and more, slightly more powerful in what they're putting out, the energy they're putting out, and you just don't want to be very close to the antenna. So, in reality, if the antenna is like right on your head versus if it's this far away, there's already a huge, huge difference because it's an inverse squared. It's a 1 over r squared. So, if you double the distance, you get a fourth of the energy.
So what about the saturation of all this? Everything is that having an inverse.
So the energies in here, what do they do to our biomolecules? Okay. Microwaves rotate. They tend to do this. Water does this in the microwave. Just spins. And it spins and it bumps into other waters, and that causes what we perceive as heating. You ever tried to put in there a piece of incredibly stale bread to try to see if you can bring it back to life? It doesn't come back to life. Okay? But if you sprinkle some water on it, it might. Okay? One of those, this was one of my graduate student days kind of things that we used to do. Anything that doesn't have any kind of moisture in it at all, microwave doesn't do anything. I can stick a rock in there, it doesn't heat up. You know, not very good. But if I stick something with water in there, it does.
Why does metal spark?
That's a different, that's kind of like, it's acting like a concentrator for the energy. And it's kind of like, microwaves are focused in certain parts, and so this kind of concentrates the energy and makes them add, and they kind of heat up too much, and they end up causing a spark. There are some videos out there that show you people doing this. There was a group in Canada that actually scientifically did all kinds of different things in there. You can measure the speed of light with marshmallows. You can do all kinds of different things inside a microwave. We've done that. We have a video of that too, of doing that. But the thing is, okay, so microwaves tend to make molecules rotate. so rotational. Okay? Infrared tends to make things vibrate. In the case of water, with an oxygen and two hydrogens on the sides, they do these kinds of vibrations, okay? Like this kind of stuff. Vibrational modes. And different energies affect different vibrational modes. Okay? They're specific. And that specificity, if we have the right instrumentation, allows us to say, oh yeah, that's water. Okay? As we get into the infrared close to the visible, and a little bit of the ultraviolet, you are causing some kind of change. Okay? Do you guys remember cis-trans transitions? Things are like this, they go like this. Okay? Those kinds of things are part of what happens with that higher energy. You can cause a cis-trans transition. You can cause a double bond to break or a triple bond to break. Okay? And if you go even higher, you can cause a greater break. Okay? And so you got cis-trans, you've got bond breaking, and then you've got totally falling apart, completely cleaving a bond. Okay? Yes.
Is the energy from the bonds breaking also negatively affect your body?
Does the energy from the bonds breaking also negatively affect your body? Sometimes that energy, so the energy used in some types of therapies, gamma ray therapy. So, just so you know, for this course, we'll primarily focus on visible light, infrared, and ultraviolet. Those will be the primary regions of the spectrum that we will be talking about. And with that, actually, I'll stop there. And feel free to email me if you have any questions about today's lecture. I will try to post these either today or tomorrow. And next week, come prepared to shed a few hairs. We're going to be doing some hands-on experiments that'll constitute the data that you'll need for your first lab report. Okay. Thank you, guys.